Hello everyone. In this video we are going to go over the lessons for week 9, which is our first week in the trees unit. Lessons for this week include L9-1 trees, 9-2 search trees, specifically binary search trees, and 9-3 balanced binary search trees, an implementation called AVL trees. Reading this week, Miller-Raynham sections 6.1 through 6.7 and 6.11 through 6.22. We're going to skip the intermediate sections 6.8 and 6.10 because this covers heaps, which we will cover during week 11. SciBooks chapters to work through 4.1 through 4.10 and MA5, which we will cover in another video. So let's start with L9-1 on trees. Now, some of what we're going to cover today and in the next lesson is going to be review from what you've learned in 122 and 132, where you covered basic trees, call trees, and binary search trees. So learn objectives for this lesson: review the basic concepts of trees, the terminology, 2 different definitions of trees, and common tree traversal algorithms, such as our pre-order traversal, post-order traversal, level order traversal, and when we talk about binary trees, in-order traversal. So let's review what a tree is. A tree is a nonlinear hierarchical data structure consisting of a collection of nodes, which are also called elements or items, and a collection of edges between the nodes. Here is an example of a tree that I have made here. The ovals in this tree are the nodes, and the lines are the links between the nodes. And there are several rules and definitions associated with trees as far as terminology goes, and we will cover these. So first, each node in a tree has an immediate predecessor, such as 5, parent, the immediate predecessor, is 2. The root node, however, which I've labeled up here root, with item 1, has no predecessor by definition, so the root is like the top of our tree. An incoming edge is from a node's parent, as in the case from 2 to 5, this is incoming to 5. All predecessors, not necessarily immediate successors of a node, are called ancestors. So anything above 5, for example, 2 and 1, are ancestors of 5. Parent nodes can have multiple immediate successors, children. In a general tree, there's no restriction on the number of children that a node can have. For example, 5, 6, and 7 are all children of the node 2. All successors, not necessarily immediate successors of a node, are called descendants. So, for example, the descendants of 1 would be 2, 5, 6, 7, 3, 8, 9, 4, and 10. A leaf node is a node that has no children. So in this example, 5, 6, 7, 8, 9, 10 are leaf nodes, as labeled here. They have no children. A tree is built of subtrees, which are trees themselves. So for example, 2, 5, 6, 7 is a subtree with 2 as the root of the entire tree, where 1 is the root. The size of a tree is the number of nodes it contains. In this case, for this tree, if you were to count up all the number of nodes, there would be 10, so the size of a tree is 10. The depth of a node is the length of its path. By definition, the root is at depth 0 because there is no incoming edge to the root node. Another example is the depth of node 2 is 1 and the depth of node 5 is 2. So for example, here is node 5. It's at level 2. Its depth from the root is 2. A level in a tree is a set of all nodes at a given depth. So for example, at level 1, the set of all nodes at level 1 would be 2, 3, 4, and level 1 consists of all the nodes that have depth 1. Nodes in a tree that are children of the same parent are said to be siblings. So for example, 2, 3, and 4 are all siblings, but 4 and 9 are not siblings. The height of a tree is equal to the maximum level of any node in the tree. So for example, in this example here, there are 3 levels, so the height of the tree is 3. Let's talk about tree definitions. There are 2 definitions that we're going to cover in this class. One is a node and links definition, and the other is a recursive definition. So the first one, a tree consists of a set of nodes and a set of edges that connect pairs of nodes. A tree has the following properties. Number one node of the tree is designated as the root node. The root node has no parent. Every node n, except the root node, is connected by an edge from exactly one other node p, where p is the parent of n. So every node has only one parent. A unique path traverses from the root to each node. Definition number 2, a tree is either empty or consists of a root and 0 or more subtrees, each of which is also a tree. The root of each subtree is connected to the root of the parent tree by an edge. We'll see implementations for each one of these definitions here shortly. Now let's talk about tree traversal. There are 3 fundamental ways to traverse a tree. The first is called pre-order, where you start at the root, you visit the current node and do something with the data, then visit all children working from left to right. Now this part here, do something with the data, in our first implementation of tree traversal algorithms, we're just going to print out the item stored in that node. So pre-order is going to print out the items in the order at which they're visited, starting with each child from left to right. Post-order, starting at the root, visit all children first, then visit the node and do something with the data. So in post-order, we're not going to print out the item at a node until after we visit all of that node's children. Number 3, level order. Starting at the root, visit all of the nodes on the current level from left to right, then move to the lower level. So level order is going to visit all of the nodes at a current level. So for example, all the nodes at level 0 is the root, all the nodes at level 2 is 2, 3, 4, and then all the nodes on level 2, 5, 6, 7, 8, 9, 10. One thing to note is pre-order and post-order traversals lend themselves well to recursive implementations, and also level order traversal utilizes a queue. Now let's talk about binary trees. The trees we've been talking about before have no restrictions on the number of children that a node can have. In a binary tree, each node has a maximum of 2 children. Each child of a node is referred to as either the left child or the right child. So we don't need to maintain a list of all children because each node has maximum 2 children, so we can fix the links to the left child and to the right child. A little bit of terminology associated with binary trees. In a full binary tree, the bottom level is full, meaning all possible slots where a node could be, a node is there. Complete binary tree, the next to bottom level is full, and the bottom level is filled from left to right. These terms in the binary tree terminology will be useful when we talk about heaps in particular. One other thing to note about binary trees is another traversal. In addition to pre-order, post-order, and level order, we also have the notion of an in-order traversal. The idea behind an in-order traversal is you start at the root, you visit all of the left children. Once you have visited all of the left children of a node, then you're going to do something with the data at this node. In-order traversals, let's remove that. In-order traversals essentially print out or visit the node after all of the left descendants of that node have been visited. So next we're going to look at implementations of binary trees. We're going to look at two different types for each of our two definitions. The first will be node and links, and the second will be recursive. So in our node and links implementation, we have two classes, a node class and a binary tree class. Here's the constructor for our node. It is quite straightforward. We're going to store the data at this node. This may also be denoted as the item stored at the node. And then we're going to have links for the left child and the right child. By default, if there is no left or right child, then we'll set those to none, as would be the case with a leaf node, but we could create a node that has either a left child or a right child, or both, or none. Here's our binary tree class. The constructor for a binary tree can accept a root node. This would be of type node. If so, we'll set root to the root node. By default, our root node will be none. This would be the case for initializing a binary tree to be empty. Our first of our non-special methods here is an is empty. It's very easy to test if a binary tree is empty. Just compare the root to none. If it is none, then this is an empty tree. So constant time complexity here. Pre-order traversal. When we want to do a pre-order traversal, we're going to implement this recursively. So our pre-order and our post-order and our in-order traversals are all going to look very similar. The only thing that's going to be slightly different about them is where our print statement is in terms of our recursive function. So pre-order traversal, as long as the binary tree is not empty, then we will call pre-order helper, passing in the root node as the current node. Now, pre-order helper is our recursive function where the work is done. Node is a parameter storing a reference to the current node where we're traversing. And as long as this node is not none, meaning it is a valid node, on a pre-order, we're going to print out the data at the node first. And then we're going to recurse the left child and the right child of this node. Now, let's look at how post-order differs from pre-order just in terms of where the print statement resides relative to our two recursive calls for post-order helper for the left and the right child. So in a post-order, we're going to recurse for the left child and for the right child before we do the print. Let's skip level order for a moment and take a look at in order, and we'll see that in order helper looks just like pre-order and post-order, except the print statement, which is what we're calling visiting a node, is in between our recursive calls for the left child and for the right child. Now, if we take a look at level order utilizes a queue. As long as the tree is not empty, then we will enqueue into our queue the root node, and we'll call our level order helper for the root node and the current state of the queue. Now, level order helper is going to make sure that the current node is not none. If it is not none, then we're going to enqueue into our queue the node's left child. As long as the right child is not none, we're going to enqueue into the queue the right child, and then we're going to recurse following the left child and the right child. So what this does is essentially as soon as a new node is encountered, it's enqueued into the queue. When level order helper is finished recursing, then back up in level order traversal, our queue is going to store all of the nodes in order. And we can just walk through each item in the queue, print out the data at that node item. So let's take a look at some example code to walk through some of these traversal algorithms. So first I'm going to build a binary tree called tree. I'm going to construct a node, and I'm going to set the root node of our tree to be this node. So if you want to visualize in your mind what our tree looks like. It is a single item. There's a single item in our tree, our root node, and it stores 1. Now we're going to make a new node where the current node's data item is 2, its left child is 4, and its right child is 5. Now we're going to set this new node to be the left child of our root. So our root is 1, its left child is 2, 2's left child is 4, and 2's right child is 5. We're going to make another node with item 3. Its left child will be 6, and its right child will be 7, and we'll set this new node to be the right child of our root node. So now our root node stores 1, our root node's left child stores 2, our root node's right child stores 3, and the left child of 3 is 6, and the right child of 3 is 7. Now we'll go through and do a pre-order, post-order, level order, and in-order traversal. And we can take a look and see what the output is here. I highly recommend that you draw this tree out and walk through what you think the output should be for a pre-order, post-order, level order, and in-order traversal, and compare your output to these traversals here. We can take a look at pre-order traversal, for example. This is going to print out the node item, the node data, in the order at which it's first visited. So our root node will be first, then we'll follow the left child, then we'll follow the left child, which is 4. So node's left child, this node's left child. And then there's no more left childs to follow. So then we follow the right child of our most recent node, which is 5, which is the right child of 2. And then we've followed all of the children of 2. So now we're going to start following all of the right children of our root node, which is 3. Then we follow 3's left child, 6, and then 3's right child, 7. Now let's take a look at an alternative implementation for a binary tree. This would be a recursive implementation. In this implementation, we're only going to have one class, and that will be our binary tree class. So here's our binary tree class. Here's the constructor, root data, left child, and right child. So by default, these will be none. Root data is going to be a tree in itself. Left child will be a tree in itself, and right child will be a tree in itself. So this is a recursive definition. Oh, excuse me, root data is not a tree. Root data is the actual data item stored for the root of this tree. Left child and right child will be subtrees. So just some getter and setter methods here. Is empty is the same. We can just test if root data is none. Now let's take a look at insert left and insert right. So suppose we want to insert to the left new data. So we're going to check if self.leftChild is none. If it is none, then we can just make a new subtree with only one node, the root node, and that root node would store new data. Otherwise, we're going to make a new binary tree for new data, and we're going to set the left child of this new binary tree to be the root node's left child. Then we're going to set the root node's left child to be this new tree. So essentially, we're going to insert this new data immediately after the root node and then copy the link for what was previously the left child of the tree. You can think of this quite similarly to how we would insert at the head of a linked list. So our tree, our outermost tree, is like our head reference, and subtrees are essentially linked together. Insert right is similar. Pre-order traversal, all of our traversals are going to be similar to our previous implementation. And let's take a look at some code to exercise our recursive tree implementation. So binary tree, root node 1, insert left, and then we're going to insert the the root node's left child to be 4, the root node's left child to be 5. So essentially we're building the same structure we built in our previous implementation, but our interface is slightly different now. Our root node's right child is going to be 3, and our root node's right child's left child will be 6, and our root node's right child is going to be